So we've been talking about individual gases, pure gases. What if we have a mixture of gases? Well, kinetic molecular theory tells us that the particles in a gas do not interact with each other, and the size of the particles is so small relative to the size of the gas sample that it's negligible. And so the implication of this is when you have a mixture of gases, the gases behave as if they were the only gas in the container. So each component in a gas mixture acts independently of the others. Maybe this analogy will work, maybe it won't. Wyoming. Wyoming is a relatively large state with the population of Fresno, right? And so there's just a lot of open space. So if you took the city of Fresno and, the people in the city, rather, not the actual city, that would be noticeable, a whole city falling into a state, someone might notice that. If you took the population of Fresno, about 400,000, and moved them into the state of Wyoming, just physically, would it really matter that there were twice as many people in the state? Would the original people, they might not even see them. There is so much space. Because when we're talking about gases, the gas particles are just moving about randomly, and they're going to be spread about equally. If you took an elevator with 10 people in it, and you stuck another 10 people in the elevator, would that impact the original 10 people? It would, because they're close together. There's not a lot of space to start with. And so adding more people is going to be really significant. In gases, there is so much empty space that you can put another gas in there, and the first gas essentially doesn't notice, because those particles are just moving along, and they're moving so rapidly that they just bump into stuff and bounce off, and they don't even notice who they've bumped into. So when you have a mixture of two or more gases, each gas acts like it's the only gas there. Gases exert pressure on their container and on their surroundings. So if we have a mixture of two gases, each gas is going to exert a pressure on the container. The container feels both of the pressures. And so the total pressure that the container experiences will be the sum of the pressure of each of the gases. It's the same idea as if you had maybe a box of apples and oranges. The oranges have a mass. Maybe there's 5 pounds of oranges and 2 pounds of apples in the box. What's the mass of the total box? It's the 5 pounds plus the 2 pounds. The masses add up. Pressures in a mixture of gases add up in just the same way. So the total pressure equals the sum of the pressures of each of the gases. In a mixture, we call the pressure of a gas a partial pressure. Each gas exerts its own pressure, which is part of the total pressure. So each gas has a partial pressure. The partial pressure of one of the components is going to be related to the fractional composition. So all of those words are hard to understand. Let's look at an example, air. We're all familiar with air. We breathe it in every day. So the air in our atmosphere is a mixture. It's about 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then some other gases in there in even smaller amounts, so we just won't even talk about those. We'll mostly talk about the oxygen and the nitrogen. So the nitrogen molecules in the air exert a pressure. They compose 78% of the mixture. They exert 78% of the total pressure. The oxygen also exerts a pressure. It is 21% of the mixture. It exerts 21% of the total pressure. Each of those pressures, the pressure exerted by the nitrogen, the pressure exerted by the oxygen, is independent of pressures exerted by the other gases. If you put another gas into that air sample, the pressure of the nitrogen and the pressure of the oxygen won't change. The total pressure will change. But the pressure of each gas is independent of the others. What do we have here? Here we have a mixture. We've got 80% helium, 20% neon. So we have 10 little atoms, in this case, 10 atoms in this picture. 2 of them are neon, 8 of them are helium. If we have a total pressure here in this sample of 1 atmosphere, 80% of that total is from the helium, and 20% is from the neon. I need to do some writing here. Let's get a pen color that we can see. So fractional composition is percent composition divided by 100. Remember we said that percent equals the part over the whole times 100. This is the fractional composition. It's just the percentage before you multiply by 100. So if this is 80% helium, then the fractional composition is 0.80 helium and 0.20 neon. Does that make sense? So 80% helium, 20% neon. We can calculate the partial pressure if we know the composition, the fractional composition, and the total pressure. So here we know that the total pressure is 1 atmosphere. This actually has a symbol. It's a capital chi, which just looks like a capital X, but it's not. So we could say that the fractional composition of helium equals 0.8. So this equation here is saying that the partial pressure of helium is going to equal the fractional composition of helium times the total pressure. Essentially, it's using percentages. What is 80% of 1 atmosphere? 0.8, right? 80% of something. How do you calculate a sale price? It's 70% off. How much are you going to save? It was originally $100. What's 70% of $100? $70. How do we do that? 70%, what we do is we take 0.70 times $100, and that is, where are the dollar sign? $70, right? 70% of 100 equals 70. We do stuff like this in everyday life. We just don't really think about it so much. So this is just writing it out. The total pressure is 1 atmosphere. 80% of the pressure is from the helium. 80% of 100 is 80, right? 80% of 1 is 0.8. So the partial pressure of helium is going to be 0.80 times that 1 atmosphere of total pressure, which equals 0.8 atmospheres. What's the partial pressure of the neon? Well, what's the fractional composition? 0.2. 0.20 times the total pressure. I don't know where I was going with that. Equals 0.20 atmospheres. What do we get if we add these two together? The total pressure back again. Okay? I don't think that went very well. Do you have any questions? Did that make any sense at all? The crazy thing about gases, which can be a little hard to get your mind around, is that what the gas is doesn't matter in terms of its pressure, volume, temperature, number of moles. In liquids and solids, what the gas is matters a lot. But in gases, it doesn't, because there's so much space in between that the size of the particles doesn't matter at all. There's no interaction between the particles, so if it's a less reactive or more reactive element or molecule, it doesn't matter. And that can be a little hard to get your brain around. So let's do an example. Here, this gas mixture contains 64% methane and 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component? Well, I'm going to abbreviate these gases M and E. So the pressure exerted by methane, that equation tells us that'll be the fractional composition of methane times, well, let's not use an X there next to the X, times the total pressure. The percent composition is 64% methane. What's the fractional? 0.64. Just divide it by 100. So 0.64 times the total pressure. As usual, I forgot to get up my calculator. So 0.64 times 1.44. This is 0.92. I'm rounding that because this has two sig figs. So 0.92 atmospheres. What's the partial pressure of the ethane? There's actually two ways we could figure that out. We could do the same process. The partial pressure of the ethane is the fractional composition of the ethane times the total pressure. So 36% would be 0.36 times the total pressure. 0.36 times 1.44. This rounds to 0.52 atmospheres. What do we get when we add those together? The total pressure back again. It's not a coincidence. In this mixture, methane is 64% of the gas. It exerts 64% of the total pressure. Ethane is 36%. It exerts 36% of the total pressure. Any questions? John Dalton was a guy who studied pressures long time ago. And there's a law named after him, Dalton's Law of partial pressures. And so what he said is the total pressure of a gas mixture is equal to the partial pressures of each of the gases added together, however many gases there are. If there's two, we're adding two partial pressures. If there's 5,000 gases, we're adding 5,000 partial pressures. And we've seen how this worked. We were doing that in this previous, let's look back here. That's really what I was doing right here. Dalton's law says that the total pressure equals the partial pressure of the methane plus the partial pressure of the ethane. And we see that that is true. We got 0.92 plus 0.52 0.52, and that adds up to 1.44 atmospheres. Looking back at that example of the air, was 78% nitrogen, 21% oxygen, 1% argon. The partial pressure of the nitrogen was 0.78. The partial pressure of the oxygen was 0.21. Partial pressure of the argon would be 0.01. You just add those all together and that gives you the total pressure. In some ways, these calculations with partial pressures are so simple that students have trouble with them because they think it's supposed to be more complicated than this, and it isn't. We're just adding them together. So here's an example. A sample of hydrogen gas is mixed with water vapor. Vapor is just another word, a fancier word for a gas. The mixture has a total pressure of 745 torr, and the water vapor has a partial pressure of 24 torr. What's the partial pressure of the hydrogen gas? Oops. Well, this is one of those word problems. So let's go through and identify what these numbers are. So here this is total pressure of 745 torr. I'm going to write that down up here. PT for total pressure, 745 torr. It says a partial pressure for the water of 24. So I'm going to call that PH2O is 24 torr. And they're asking what's the partial pressure of hydrogen. So we're dealing with partial pressures here. There's no mention of fractional or percent composition or anything like that. So we're going to use Dalton's Law. So Dalton's Law says that the total pressure equals the pressure of I forgot what we're dealing with, the water, plus the partial pressure of the hydrogen. This is the one we're trying to find. So we just need to rearrange this equation. And students sometimes, I don't know what happens. We'll just call it a brain fart. They get to this equation and they freeze up. It's adding and subtracting. So if I want to get pH2 by itself, I'm going to subtract H2O from both sides. So if I subtract pH2O from this side, pH2O minus pH2O is 0, right? And all I'm left with is pH2, the partial pressure of the hydrogen. And if I do something to one side of the equation, I have to do it to the other side. Well, over here, nothing cancels out, but that is equal to the total pressure minus the pressure of the water. This is the same idea as Johnny has 10 apples, and he gave 2 to Susie. How many did Billy get if he gave the rest to Billy? Right? We can do a question like that, but then when we look at partial pressures, we freak out. It's the same. So the partial pressure of the hydrogen just is equal to the total pressure of 745 minus the 24. You can calculate this with any gas unit, but when we're subtracting, those units have to be the same because you can't subtract things that are different units. So we've got 745 minus 24, 721. That's the pressure exerted by the hydrogen. Any questions? This whole idea of partial pressures is important if you're going deep sea diving or scuba diving. I'm not going to test you on this, but I think it's kind of interesting. I'm just going to go through it real quick. So our lungs perform best at a partial pressure of 0.21 atmospheres of oxygen, which not coincidentally is the partial pressure of oxygen in normal air. I'm sorry, I'm distracted by the two people kissing outside the window. Feel free to turn around and stare at them. Right? It's hard to talk about partial pressures. There's a little too much lip pressure going on there. If we go to higher elevations, the total pressure of the atmosphere decreases, and the partial pressures of all of the gas components of air also decrease. What happens to your physical ability when you go to high elevations? You get out of breath more easily, right? Especially if you're not accustomed to it. You can get altitude sickness because you're not getting enough oxygen. So the partial pressure of oxygen decreases. This is why people who climb really, really high mountains have to be careful, because there's a condition called hypoxia, which is oxygen starvation. And severe hypoxia, pressures of oxygen less than 0.1 atmospheres, can result in death. Basically, you suffocate even though there's air around you. We sometimes say the air is thin up in the mountains, right? So here's a little graph showing at the surface, we've got, this would be 100% oxygen, a partial pressure of 1 atmosphere. This is getting into the range of hypoxia, where you have a partial pressure of less than 0.21. And then if we go to too much oxygen is also dangerous. Oxygen can be toxic. Okay, so just like water, we need water to live. We will die without it, but if we get too much, we'll also die. Everything is good at a certain level. Well, take that back. Okay, we have this idea of chemicals as being toxic, right? Ooh, toxic chemicals, I want chemical-free bread or whatever. But all matter technically is a chemical, and natural things are dangerous too, and things that are good at some levels are dangerous at other levels. And so it's all in amount, right? Kind of a moderation in all things. If you have it at the right level, it's okay. It's good. So oxygen toxicity happens at partial pressures above 1.4 atmospheres of oxygen. That's not going to happen just, walking around Tulare, right? It's not going to happen. But if you go deep sea diving and you don't know what you're doing, you're breathing pressurized air, you can get into a situation where you have oxygen toxicity. Symptoms would include twitching, tunnel vision, convulsions, and eventually death. So at the surface, the pressure of the air that you're breathing is 1 atmosphere. And so 21% of 1 atmosphere is 0.21 atmospheres. If you are diving at a depth of 30 meters, the pressure has to be greater of the air that you're breathing through the tank, because you need a certain amount of air pressure to be able to expand your lungs against the water pressure exerted by being 30 meters below the surface. So the total pressure is 4 atmospheres, and now 21% of 4 atmospheres is 0.84 atmospheres. And so if you use just compressed air and go deeper and deeper into the ocean, you're getting a higher and higher partial pressure of oxygen, and eventually you can get to a point of oxygen toxicity. Pressurized air also has an increased partial pressure of nitrogen, which isn't good for you either. Well, actually not. So have you heard of the bends? So deep sea divers who come up who surface too rapidly get a very painful condition called the bends, which I think is named because you double over in pain. Okay, that's not what this slide's about. Sorry. This is nitrogen narcosis. Sorry. It's also called rapture of the deep. Feels like being tipsy. That's what they say. I don't believe in going that far below water. But that's when you get too much nitrogen in your lungs, when you're breathing a pressure that's too high. So if you're going deep sea diving, they need to use a different combination of gases so that when they get down to those depths, they don't end up with nitrogen or oxygen toxicity. And so one common mixture is called heliox. It's a mixture of helium and oxygen. Breathing helium doesn't have that effect on us that breathing higher concentrations or higher partial pressures of oxygen and nitrogen do. And so it acts as a very inert gas to dilute the oxygen. Of course, it would make your voice really high, like Mickey Mouse. But when you're scuba diving, nobody can hear you talk, so then you don't get the fun of that. I just want to know. Okay, so I mentioned the bends and nitrogen. The problem is when you're breathing compressed air, you get a higher concentration of nitrogen into your blood, and then if you surface too quickly, the nitrogen actually comes out in bubbles of nitrogen in your blood. Does that sound like that would be a pleasant experience? No, it's a really painful experience. So that pertains to actually a different topic, so I'm sorry I brought it up. But let's look at this problem. Enough rambling. So a diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres, which is ideal. What would the total pressure have to be? So that one's already labeled for us. PO2 is 0.21 atmospheres. This 5% oxygen. So the equation that we're going to use here is, we know that the partial pressure of the oxygen equals the fractional composition of the oxygen times the total pressure. So this is related to the fractional composition of oxygen. So 5% divided by 100 would be 0.050. It's the fractional composition. In this question, we know what PO2 is, but we don't know what PT is. And so we need to rearrange the equation. And to do that, we divide both sides by chi, and we end up, the total pressure is going to equal the partial pressure of the oxygen divided by the fractional composition of the oxygen. So that's 0.21 atmospheres divided by 0.050. There's a reason that they make you take hours and hours of instruction before they let you go scuba diving. And that's so you don't kill yourself. So that would be a partial pressure of 4.2 atmospheres. So if your heliox has 5% oxygen, then you want to be running the total pressure at 4.2 atmospheres to be in a good place of breathing and not dying. Any questions? Collecting gases over water. This is what we did in lab last week. Because we're behind in lecture, it was a little confusing because we hadn't talked about this yet. So, collecting a gas that's given off by a chemical reaction can be a little tricky. This is not exactly how we did it in lab, but it's similar. Here we've got the reaction going on in a test tube. We've got this closed off with a stopper, and then we have a tube leading into a bucket of water and going up into this inverted beaker full of water. As the gas is pushed out of this test tube. It's generated by the reaction between zinc and hydrochloric acid. The gas wants to escape, and so it's going to push through here, and it's going to come up through the water, and it's going to get trapped here in this inverted beaker. As it comes in and fills up this, it's going to displace some of the water. And we saw this with the eudiometers. We had the reaction occurring in the base of the eudiometer, and then the hydrogen gas bubbled up, and we saw the water level in the eudiometer go down as the hydrogen filled it up. The thing about collecting a gas over water is that you don't just get the gas you're interested in. You also have water vapor, because water evaporates, right? And so in this little environment here, we have an empty space, and we have water and liquid water, and some of that liquid water is going to evaporate. And so what we end up with is a mixture of gases, the gas we're interested in that we were collecting, plus water in the gas state, water vapor. And so we use Dalton's Law of partial pressures to figure out what the pressure of our gas of interest is. What's really convenient about this is the pressure of the water vapor, which we call the vapor pressure of water, only depends on the temperature at which the gas is collected. So this is going to depend on the temperature of this water and the space above it, which are most likely going to be the same temperature. So we measured the temperature of our water. That gives us the temperature of this as well. And the vapor pressure of water depends only on the temperature. We had a table, something like this one, and we see that as the temperature increases, the vapor pressure of water increases as well. The warmer the water is, the more gas vapor there is above it. Gas vapor, more water vapor. So we could do a problem like this. Hydrogen gas was collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen gas? What did I do that for? Well, let's look at Dalton's Law. The total pressure, we've got hydrogen gas here, P, so there's a partial pressure from the hydrogen. And anytime you see collected over water, that means there's also water vapor. So the total pressure is the hydrogen pressure plus the water vapor pressure. We can measure the total pressure, so we know what this number is. This is the one we're trying to find, the hydrogen. And this one depends only on the temperature. We know the temperature is 25 degrees Celsius, so we can go look this up on a table, and we know that the partial pressure of the water is 23.8. Be careful with your units, millimeters of mercury. So here the partial pressure of the hydrogen will be the total pressure minus the pressure of the water vapor. So total pressure was 758 millimeters of mercury. And the water vapor pressure is 23.8 millimeters of mercury. So 758 minus 23.8. So the hydrogen is giving a pressure of 734 millimeters of mercury. That's a 7. Any questions? This is a calculation you need to do for the lab that we did last week. We measured the volume and temperature of the hydrogen gas, and we set it up so that the total pressure of the gas was equal to the atmospheric pressure, which I wrote on the board and you should have written down. So you take that total pressure and you subtract the vapor pressure of water, which you find from the table, and your temperature.